Hello students, in this video we will try to understand the phenomenon of Raman effect. So as you might be already familiar with the contributions of C.V. Raman, Raman effect is the major contribution by Sir C.V. Raman which resulted in awarding him with the Nobel Prize. So in this video we will try to understand the quantum theory of Raman effect, how the quantum mechanical theory could explain this phenomenon. So first let us try to understand the experimental setup of Raman effect. So as you already know, the blue color of the sea was explained by Rayleigh as Rayleigh scattering. So Rayleigh scattering is the process in which the light or the photons falling on a material is scattered back with the same frequency or the same color. So this is an elastic scattering. So light waves falling on a material will be scattered with the same energy, the same frequency and the same color. That is happening in the Rayleigh scattering. But when we come to Raman effect, he prepared an experimental setup. So let us study that setup first. He filtered the sunlight to produce the violet light. So using violet filter, C.V. Raman was able to produce violet light. Now when we say violet light, you have to remember that the color is actually related to the frequency. So when we say that violet light is being produced, you have to remember that a light wave of around 400 nanometer wavelength or corresponding frequency is being produced. Now this violet light was scattered through a liquid medium and the resultant lights were observed by C.V. Raman. So he used a green filter to study the resulting light. He was able to produce or he was able to find green light on the output side. So what is happening here? The incident light that falls on the liquid is simply violet. But on the output side, we have lights of violet color as well as green color. So using green filter, he filtered this violet component and he observed the green component. The green component or the green colored light is not present in the incident light, but it is being produced at the output side. So something might be happening within this scattering setup that actually shifts the color or the frequency of the incident light. So that is being studied under Raman effect. So we can define Raman effect as the phenomenon in which when a beam of monochromatic light is passed through organic liquids such as benzene, toluene or carbon disulfide, the scattered beam consists of other frequencies in addition to the incident frequency. That is the phenomenon of Raman effect. So as you can see here, this is the incident frequency that will be of one particular color, say violet, and after it is being scattered by this liquid such as benzene, toluene, etc., the resultant light beam that is produced actually consists of additional frequencies. As you can see, nu L plus nu 0, nu L minus nu 0 and so on. These frequency lights are being produced through this scattering phenomena. That is studied under the Raman effect. So as you can see here, when light beams are made to fall on a sample and being scattered, there are additional components of different frequencies that are being generated. Those light waves that have the same frequency or the same energy as the incident light is the Rayleigh scattered light, and those light rays that have different frequencies or different energies are called Raman scattered light. How energy and frequency are related? We have the equation E equal to h nu, which is the quantum mechanical equation under the assumption that the energy is quantized in the case of an electromagnetic wave. So we have E equal to h nu, so energy will be related to the frequency. So here we can see the incident light of having a particular energy or a particular frequency is falling onto the sample, and after it is being scattered, there is a Rayleigh scattered light which has the same energy or the same frequency, and there are Raman scattered light which has higher frequency and lower frequency, or higher energy and lower energy. So this is what happens in Raman effect. Now let us try to understand the principles that lies behind this phenomenon, how this process happens. So in the Raman scattering, according to the quantum mechanical theory, what happens in this process of emitting different frequency or different colored lights through scattering process can be explained as indicated in this figure. So we know when photons are made to fall onto a material, suppose the frequency of the incident photon is nu 0, so that the energy E0 will be h nu 0. Sometimes this sample or this molecule might scatter off this light with the same frequency itself, so that the output energy is same as that of the input energy. And these kinds of scattering will result in Rayleigh scattering, where the input color and the output color are just the same. So as you can see here, this picture depicts the excitation process. So initially the energy of the molecule which is scattering of the light is at this level, corresponding to frequency nu 0. So the incident photon will excite this particular molecule to a higher level, and after it is being excited, after a very small time, it will re-emit this photon, thereby getting de-excited to the initial level. So in this process, the net energy gained by this molecule is 0, because it started from here, it got excited up to a different level, then it emitted the photon back and got de-excited to the same initial level. So what is the energy gain or loss by this photon? The photon has gained or lost no energy or zero energy. So that is why in the Rayleigh scattering process, the incident photon has the same frequency as the reflected or scattered photon. There is no color change in this process. A difference in frequency causes color change. So the incident color and the scattered color of the light will be just the same in the Rayleigh scattering process. Now what actually happens in the Raman effect is that the molecules that are taking part in the scattering process are actually contributing some energy or taking away some energy from the incident photon. So suppose the incident frequency is nu 0, the incident energy is E0, and the molecule is scattering off this light, suppose with a different frequency, say nu 0 minus nu, so that the sample of molecule has actually absorbed a small amount of energy, say E0 minus E. So in this process, the photon has lost some energy. It has actually supplied some energy to the incident molecule, to the sample molecule. So the resultant energy of the photon will be E0 minus E. E energy is given to this molecule. So what is E0 minus E? It is h nu 0 minus h nu, which is equal to h into nu 0 minus nu. So the frequency of the scattered light will be nu 0 minus nu. So that is why the scattered light is having a different frequency. Now let us try to understand it in terms of these excitation levels. First, the molecule or the molecule of the liquid that we consider was at this level, this energy level. After the photon hits this particular molecule, it is getting excited to a higher level, and after a brief time it is re-emitting the photon and getting de-excited, but it is not going back to the initial level. It is actually keeping a little bit of energy. This much energy is being gained by this particular molecule. So from where does this molecule absorb that energy? From the incident photon. So the incident photon lost a little bit of energy to the sample molecule, and the photon that is re-emitted will be of lower energy and hence of lower frequency. That is why we see a different color that is being scattered off in the case of Raman scattering. So in this particular example, we saw that the incident photon lost some energy, and as a result, the scattered off photon will have a lower frequency compared to the incident photon. And these kinds of scattering or these lines are often called Stokes lines. So the Stokes lines actually have lower frequency when compared to the incident frequency compared to the parent line. Now coming to the anti-Stokes lines, in that process a second type of scattering can occur. In this case, the sample molecule will be already at an excited state. Now the incident photon, which has a frequency nu0 and an energy E0, might be scattered off, but this excited sample of molecule can actually contribute some energy to the photon, so that the energy of the photon is increased by a small amount. So E0 plus E. Suppose E0 is h nu 0 and E is h nu, then we have h into nu 0 plus nu. So the frequency of the emitted photon is nu 0 plus nu, a frequency higher than the incident frequency. So in this process, energy has to be supplied by the sample molecule to the photon, so that the output energy is higher. In the earlier process, the energy were taken away by this sample molecule from the incident photon, so that the output energy was lower. So this contributed to the Stokes line, and this phenomenon of contributing energy to the incident photon contributes the anti-Stokes line. So they will have a frequency higher than that of the incident photon. So as you can see here, if we study the excitation level, initially the parent sample of molecule was at this energy level at an excited state. The incident photon excited it further to a higher level, and from there the photon is being emitted and it is de-exciting into a lower level. The molecule is de-exciting to a very lower level. So there is a net loss of energy here by the molecule, and that loss of energy is actually gained by the emitted photon. So E0 plus E will be the energy of the emitted photon, and nu0 plus nu will be the frequency of the emitted photon. So this emitted photon will have higher frequency when compared to the incident photon. So that contributes the anti-Stokes lines of the Raman scattering process. Now if we draw the frequency curve, that is, if you plot the frequency along the x-axis and the corresponding intensity along the y-axis, we can see that there is a component in the output side. We have the Rayleigh scattering process, which results in the light that is observed at the original frequency itself, and there are additional lines that are being generated. So these lines having frequency lower than that of the original frequency contribute the Stokes lines. So as you can see here, frequency is marked towards the left side and wavelength is marked towards the right side. So this positive side actually corresponds to lower frequency. So from the original frequency, we can see certain lines have lower frequency, and those are called Stokes lines. And there are also some lines that have higher frequency than the incident frequency, and they actually contribute or form the anti-Stokes lines. And as we have seen, Stokes lines are produced due to the gaining of energy by molecules, thereby losing of energy by photons, and anti-Stokes lines are formed by supplying of energy to the photons by the excited molecules. So this is the process of Raman effect. This is how quantum theory explains the Raman effect process, Raman scattering, based on how photons interact with the sample molecules, and based on the equation E equal to h nu, we could explain the process of Raman scattering. I hope this portion is clear for you. Thank you.